Okay, so thank you everyone for attending today's Foxconn Quantum Computing Seminar. Today we have the pleasure of having Angelos Pelecanos, who will tell us about mixed state tomography reduces to pure state tomography. So Angelos is a PhD student in computer science at UC Berkeley, where he is co-advised by Professors Shafi Goldwasser and John Wright. And his research spans theoretical computer science with a focus on quantum learning theory and cryptography. And he holds master's in engineering, bachelor's degrees in computer science and engineering and mathematics from MIT. Yeah, so Angelo, the floor is yours.
Thank you very much for the kind introduction and of course for the invitation to speak here. So today I'm very happy to be talking to you about some recent work on how mixed state tomography reduces to pure state tomography. And this is joint work with an amazing set of collaborators from UC Berkeley, Jacques Pilecki, Tang, and John Wright. So the first half of this talk will be about learning pure and mixed states and the differences between them. Let me first give you the setup of quantum state tomography. So here we have an experiment, quantum experiment. We run the experiment and it outputs some quantum state raw. We want to learn something about the state, so we perform some measurement and it gives us some information. Now, of course, the information collapses the state, so we may want to rerun the experiment multiple times. We get multiple copies, we measure them, and we get even more information about the state. So overall here, we're given n copies of a quantum state raw, and our goal is to learn something about the state. I will say as a short remark here that what I described corresponds to measuring every copy of the state separately. This is what we will refer to as unentangled measurements. But here we're really interested in the information theoretic limit. We really want to understand what is the maximum information we can get about state. So we will consider the strongest type of measurements, which is entangled measurements, where now we're going to run our circuit, our experiment. We get all of the copies together, and we perform one big entangled measurement on all of the copies together. And this will give us hopefully a lot of information about raw together at once. So given the setup, perhaps the most fundamental basic question is what we will call quantum state tomography, and sometimes to distinguish vanilla quantum state tomography, in which we're interested in learning the full description of the state raw. However, some more problems will make their appearance, including shadow tomography or K-entangled measurements and quantum metrology. So let's specify now for quantum state tomography. We have an experiment, we get our n copies, and let's say we have a state that lives in d dimensions and has rank r. We get n copies of the state, and now our goal is to output a classical description of a state rho hat, such that the distance of rho from rho hat is at most epsilon, with probability at least 1 minus delta. A few remarks. D here for us will be the trace distance or the infidelity, which I define as 1 minus the fidelity. And we will be interested in understanding what is the minimum number of copies n that we need to learn a good description of the state. We will also be interested in implementing such an algorithm, such a tomography algorithm, using a number of gates that is polynomial in the optimal number of samples. Maybe two remarks in addition. Here we have a rank R state. Since we care about pure states, of course, pure states correspond to rank 1 states. And when it comes to comparing trace distance and infidelity, it holds that infidelity is a more stringent measure than trace distance. So whenever you are able to learn in infidelity, this also implies that you can learn in trace distance. So the title is Pure State and Mixed States. So let's see what we know about pure state tomography, which is the special case of rank 1 states, and what we know about the generic question of when the rank is between 1 and d. So in the case of pure states, we have sample optimal algorithms since the 1990s. Whereas for mixed state tomography, it took until 2016 for the first sample optimal algorithms to be proven. In the case of pure state tomography, a number of samples that is theta of d suffices. And this is because a pure state can be described by its d amplitudes. So roughly this many samples is sufficient. In the mixed state tomography case, we have a rank R state now. So we need RD number of parameters roughly. So RD number of samples suffices in that case. In the pure state tomography case, we know that performing an entangled measurements, which is again measuring every copy separately, is enough to achieve a sample optimal algorithm. Whereas when we're interested in mixed state tomography, to get sample optimality, we need to perform entangled measurements and measure many copies at once. Moreover, for pure state tomography, we have algorithms that are computationally efficient, and this is polynomial in the number of samples required, whereas we do not know how to efficiently implement mixed state tomography algorithms. Finally, pure state tomography is a more conceptually simple task, and it has conceptually simple algorithms that one can perhaps teach at a class, whereas to describe and analyze the currently known sample optimal mixed state tomography algorithms, you require non-trivial excursions into representation theory, and it's really not as a clear picture as the pure state case. So given the current state of affairs, it makes sense to conclude that pure state tomography and mixed state tomography are two very different beasts. And the main goal of today's presentation is to argue that actually mixed state tomography and pure state tomography are very related. In fact, there exists a reduction that takes you from mixed state tomography to pure state tomography. And the main ingredient of this reduction is an efficient procedure that generates random purifications of mixed states that was recently introduced by Tang, Wright, and Zhandry. And so this talk is using this purification in mixed state tomography tasks. And as I said before, we will not restrict our attention to vanilla state tomography, but we'll consider some more tasks as well. And we will see how one can recover or even improve upon all known mixed state tomography results. And so this should perhaps persuade you that studying the random purification channel is the object that is required for mixed state tomography. So this is the agenda for today. We can start by defining purifications. So what is a purification? We have a pure state that I will call ket raw on registers A and B. So we say that this is a purification of a mixed state raw on registers A if when you throw the second register out in the trash, what remains is the mixed state raw. Formally, we say this as when you trace out the second register of the pure state, you get your desired mixed state. So formally, let's say we're given a generic rank R mixed state that you see there, then there's a very natural purification in which you increase the size. The second register has dimension R, where R is the rank of your state. And in the second register, you store the index of the eigenvector psi I. And you can verify that when you trace out the second register, you get the desired state. Of course, there is no reason to restrict your attention to just ket I in the second register. There is a more general purification in which you can put in the second register any UI as long as U1 up to UR, where recall R is the dimension of the second register, is an orthonormal basis. So given all of this discussion about how nice pure state tomography is, it would be great if, given copies of a mixed state raw, we could generate this nice object, a purification, and kind of reduce mixed state to pure state. Unfortunately, doing this the naive way is impossible. In particular, let's assume for the sake of contradiction that there exists a map that maps any mixed state row to some fixed purification ket row. And note that I'm bolding the word fixed for a reason that we'll see in a bit. So we'll see how this is impossible. In particular, let's say that you choose your two favorite mixed states, rho and sigma, and this map must map them to some fixed purification that we call ket bra rho and ket bra sigma. But now by linearity, this map should also map the midpoint of your two favorite mixed states to the midpoint of their purifications. And that should itself be the midpoint of the mixed state you started with. However, you can see that the midpoint of two pure states is not necessarily a pure state. So such a map does not work. So we can't have a channel that maps one copy of rho to any fixed purification. So now you may ask, well, you only gave me one copy, you want an exact purification, you're being a bit too strict. Well, some recent work actually studied the more general setting where you're given many copies of a state and it suffices to produce some approximate purifications, and they obtain some pretty strong no-go theorems. Given the state of affairs, it may be perhaps surprising that this recent work by Tang, Wright, and Zhandry showed how you can construct a purification as long as you're okay with not constructing a fixed purification, but some random purification. And their theorem is the following. There exists a channel that we will call purify for this talk that takes n copies of a rank R mixed state rho. And here I want to clarify that this holds for all values of n. N could be 1, n could be very large. And this thing takes n copies of a mixed state, and it outputs out, again, n copies of a random purification. And recall what I defined to be a generic purification. Essentially, it outputs a generic purification, and the randomness is in the choice of the random orthonormal basis U1 up to UR. Schematically, you are giving it n copies of the mixed state. It randomly chooses orthonormal basis, kind of this green state, to put and purify, and then it outputs n copies of the same thing. So it is very important that the UIs are chosen to be consistent among the n copies. Finally, and one of the key ingredients here as well, is that you can implement such a channel to diamonds distance delta in polynomial time. So it's also an efficient channel that we can use, using quantum circuits. Oh, I see there is a question in the audience.
I'm just curious. Suppose n equals 1. Is the output state a tensor product state?
We will actually do the n equals 1 example in the next slide, if you're okay with waiting. Oh, yeah, good question.
So
By the way,
I couldn't hear the question. Do you mind repeating the question?
So maybe you, Jay Tyson, if you want, you can repeat the question.
Oh, if n equals 1, I wondered if the output was a tensor product state or not. I assume it's not, but I don't know.
We will see. We'll see. We'll work it out exactly. Yeah. I should mention, by the way, that of course, feel free to interrupt me with questions at any time. It would be great if it is interactive. Okay, so I think that's all I wanted to say. So we will call this the random purification channel for this talk. And yeah, as I mentioned, we will see an example of this. And in particular, let's try to understand this mysterious expectation of a random purification, tensor n. And the n equals 1 case is actually quite instructive, and we can work it out. So we're given one copy of a mixed state. We output a random purification of the state. I have here the definition of what I mean by random purification. And let's just do the math. So expectation of ket bra of rho, I'm going to expand ket of rho, given the definition there. Now we're just going to put together the summations. And I also moved the expectation inside the summation. And because here the only random thing is the UIs, I put the expectation all the way up to the UIs. All right, so now we're going to compute the expectation. Note that the UI and the UJ are just random orthonormal bases. So if I and j are different, this becomes 0. Otherwise, if I and j is the same, we get a random rank 1 matrix, so it becomes the maximal mixed state over dimension R. Okay, so now our double summation will collapse into a summation over just 1i. And this is what we get. And then note that the first tensor factor is exactly the original state we started with. So actually, purifying one copy is just appending a maximally mixed state in the second register, which is kind of useless. Well, maybe on the high level it seems useless. Yeah, maybe I can pause here since there was a question about this to digest. Okay, and maybe I should mention also that that was an easy derivation. However, the general case, I can't really show it since it includes a little bit of representation theory, and it's not very good for presentations. Yes. Okay, so now, given this nice random purification channel, we have the tools to use it to obtain simpler, faster, and mixed state tomography algorithms that succeed with high probability. So we introduce a mixed state to pure state reduction that uses the random purification channel. In particular, let A to be your favorite pure state tomography algorithm. Then we can lift this into a mixed state tomography algorithm using the following procedure. You're given, of course, n copies of a mixed state. You're going to run the purification channel, and this will give you n copies of the same random purification. Now you have a pure state purification, so you will run your favorite pure state tomography algorithm A on it, and this will give you an estimate rho hat of the pure state. But you want an estimate of the traced out state. So, well, you can just trace out the second register of KED of rho hat, and you're going to get an estimate of the original mixed state. Okay, so we can look at, let's do a quick sanity check. So here, the first step maps rho to a random purification, KED rho, that lives in an RD dimensional state, right? Because now we have a second register that's R dimensions, so the whole thing is RD dimensions. And we know that at the second step, when we run pure state tomography, we need a number of samples that scales roughly with the dimension, and here it's RD. So using RD samples roughly, we're going to get some KED rho hat that's close to KED rho. And then finally, when we trace out, if we squint our eyes and we say that KED of rho hat is equal to KED of rho, we see that tracing out gives us exactly what we want. Okay, so on a high level, it seems that we can get R times D sample complexity for mixed states. So let's do this a little bit more carefully. To do this carefully, we have to be more explicit, and in particular, we need to decide on a pure state tomography algorithm A to use. And actually, we will use two algorithms that are sample optimal that I will introduce right now. The first one is what we call the GKKT algorithm. This algorithm uses unentangled measurements, which we know are sample optimal for pure state tomography. It performs the uniform POVM, if you know what that is. And moreover, we know how to implement this efficiently using K-designs. This is the guarantee that we know from this algorithm. For now, maybe just observe that a number of copies that scales with D of a pure state psi, we get some output psi hat, such that with probability 1 minus delta, the overlap of psi with psi hat is 1 minus epsilon at least. And in addition, this algorithm can be implemented efficiently. That's all we need for now. I would say we use this just because it has an efficient implementation it will imply an efficient implementation for mixed-state tomography. However, to obtain the rest of our applications, we will need kind of a better, stronger algorithm that is the one that I'm introducing now, which is by Hayashi. This one uses entangled measurements over the whole symmetric subspace. And there is a formal sense in which it is the optimal algorithm for pure state tomography. However, we don't know how to implement this algorithm yet. And as I said, we will use this in the second half of the talk, to get the remaining applications that we're interested in. All right, so let's return to the first GKKT algorithm, and let's see what happens when we put it through the reduction and we get a mixed state tomography algorithm. So recall the algorithm. We're given n copies of states. We run purified to get n copies of a purification. So now we run the GKKT algorithm, and recall from the guarantee of this algorithm that with probability 1 minus delta, we're going to get some pure state, rho hat, such that the overlap of rho hat with rho is at least 1 minus epsilon. Of course, to do this, we need to choose n to be the sample complexity of GKKT when it works on pure states that live in an RD dimensional space. So let's say we choose that n, so we get this guarantee. So now we will do the third step, which says you have to trace out the auxiliary register, and then the fidelity between the original state rho and our estimate rho hat is at least the fidelity of the purifications, since tracing out can only increase the fidelity by data processing. And the fidelity of pure states is equal to the overlap squared of the pure states. And this, by the GKKT guarantee, is at least 1 minus epsilon. In conclusion, we get the following theorem. Given n copies of a rank R state rho, our mixed state tomography algorithm that uses GKKT outputs a mixed state rho hat such that the fidelity is at least 1 minus epsilon, or the infidelity is at most epsilon. And with probability 1 minus delta, when the number of samples n is RD plus log 1 over delta divided by epsilon, and we will see the sample complexity in detail in the next slide. But another point to observe is that this algorithm can be implemented efficiently. This is because it has 3 steps. The first step, the random purification channel step, can be implemented efficiently. The second step is the GKKT algorithm, which can also be implemented efficiently. And the final step is just tracing out, which is also easy to do. So now it's time to focus on the sample complexity of this algorithm. So what is the sample complexity of mixed-state tomography? Prior to this work, we had 2 competing upper bounds. The first one is by Heidel from 2016, where they show that up to some log factors, RD plus log 1 over delta divided by epsilon samples suffice to reach infidelity epsilon. The other upper bound is from prior work of ours with the de-Bias-Kaus algorithm, in which we show that without any log factors, RD times log 1 over delta divided by epsilon samples suffice. Moreover, there is a lower bound of RD plus log 1 over delta divided by epsilon. And maybe a fun fact here is that the work of Yuan from 2023 that gave this lower bound also employs a similar mixed to pure state strategy. So the bound that we just achieved now is exactly matching the lower bound that is known and improves upon the known upper bounds either by shaving log factors or by going from a multiplicative dependence on the log 1 over delta to an additive dependence. So that's great. So we get the optimal sample complexity in all 4 parameters. And allow me here to maybe make a quick remark about this confidence parameter delta. So this confidence parameter is, of course, very important. It appears whenever we want to make a statement of the form with 99% probability or 95% confidence interval. And actually, it holds that whenever you have an algorithm that succeeds with 99% probability, this corresponds to delta being 1%, you can actually boost it by incurring a multiplicative, by increasing the number of samples by a multiplicative factor of log 1 over delta to any 1 minus delta success probability. And it's not a hard procedure. Essentially, you repeat your algorithm log 1 over delta times, and then you take some type of majority vote. However, we can see that the Wright dependence is additive on log 1 over delta. And this gives the following remarkable fact that because the RD factor on the numerator is gonna always dominate the second factor unless delta becomes exponentially small in RD, then the number of samples that you need to achieve 99% success probability is essentially the same with the number of samples you need to achieve 1 minus exponentially small in RD success probability. So that's a fun fact. If any one of you is ever interested in doing a union bound over exponentially many things, you can keep this in mind. It may be helpful. Okay, so we can return to our algorithm. And to summarize, we have a simple and intuitive algorithm, which is just reduced to pure state tomography trace out. This algorithm can be implemented efficiently, which we didn't know how to do before for sample optimal algorithms. And finally, it achieves the optimal sample complexity in all 4 parameters. That's great. And maybe a quick remark is that even though we know that we need entangled measurements to achieve sample optimality in mixed state tomography, this sample optimal algorithm only required entangled measurements in the produce the purification phase in the first step. The second step, since it uses GKKT, it was only an unentangled measurement. So this is a curious fact. So this concludes the first half of the talk. We're gonna a little bit shift gears and go into new unbiased estimators in the second half. So maybe that's a good stopping point if there's any questions or to take a breath before the second half.
Is this purification channel something easy to write down?
Yes. So there is. It's even easy. Well, I think it's easy if you're okay with doing some basic Schur-Weyl duality and Schur-Lemma stuff. It's easy to even describe the algorithm. But also it has been some follow-up work by Ludovico Lamy and his group gave a way to kind of characterize it as an average over, gave a way to describe its Krauss operators. So it's not too hard to write down. And the papers that explain it do a good job. Okay, so we can start the second half then. I think we're doing great with time, which is about unbiased estimators. So recall the original setting of quantum state tomography, where we want to learn something about RAW, and we spent the first half talking about this vanilla problem of learning the classical description of the state. But there is more tasks that are very fundamental and we still need to study. One of them is what we call K-entangled tomography. This is again the problem of writing down classical description of the state RAW, but now you're only allowed to measure K copies at a time. And of course, this problem is very timely, especially now in the NISQ era, because near-term quantum devices may not be able to implement large entangled measurements because of hardware constraints. Moreover, it interpolates very nicely between the two extremes, the K-cos1 unentangled measurements, where you measure every copy separately, and the other extreme of I measure all of the copies together. And on a more philosophical point, it helps us understand what is the information theoretic limit, how much can we understand using big measurements, small measurements, and so on. The second task that we will consider is the task of shadow tomography. Perhaps shadow tomography doesn't need an introduction, but let me still introduce it. We're given M observables, O1 up to OM, And our goal is to estimate the trace of our state with all of these observables simultaneously up to some error epsilon. And this problem, of course, is so generic that it has many applications in learning, in testing, and so on. And it's a very desirable problem because now we're not interested in learning the whole state, the whole D by D density matrix, but we're only interested in some observables. So this can very often be done using much less samples than full state tomography. Finally, a third problem that we tackle is in the area of multi-parameter quantum metrology, where one is given a state rho that is parametrized by real vector theta. And our goal is to estimate this parameter theta. And this problem, again, has a very general setup, and it's very useful in understanding information theoretic limits and fundamental physics tests. So the first two of these very important tasks were the focus of some recent works by Shen, Li, and Lu. And in their work, they identified the following bottleneck in getting good algorithms for these tasks, which is the lack of unbiased estimators for entangled tomography. Let me be a little bit more specific with what I mean with unbiased estimators. For entangled tomography, an estimator rho hat is unbiased if the expectation of rho hat is equal to the state we want to learn, rho. And actually, unbiased estimators have many desirable features. Don't take my word for it. Voinov and Nicolin say that unbiasedness is one of the most important properties of statistical estimators. And actually, these two mathematicians like unbiased estimators so much that they have written a multi-volume book on them. And in their book, they collect roughly 1,000 unbiased estimators for different statistical parameters. So here is some theoretical motivation on why we should try to find unbiased estimators for entangled tomography. It is such a fundamental problem, we should try hard to get some unbiased estimators. And of course, maybe a more practical motivation is that having an unbiased estimator gives very simple algorithms for the basic quantum state tomography tasks that we have outlined before. And let me explain what I mean about the simple algorithms that we can get. Maybe let me add to the description of an unbiased algorithm that being unbiased is not enough. We also want to measure the quality of an unbiased estimator, and that quality is captured by its variance, how much it varies around its mean. So let's look at our first application of K-entangled tomography. If we had an unbiased estimator, how can we estimate the state when we are only allowed to measure K copies at a time? Here is an idea. We get our n copies of rho, and we divide them into m groups of K copies each. So here is the figure. We split them. We get K copies in each group. So now we do unbiased tomography on each group separately, which is allowed since we're allowed to do K-entangled measurements. This will give us estimators rho hat 1 up to rho hat m. And now to put them together to get one estimator, we just average them together. Since the estimators themselves are unbiased, their average remains unbiased. So that's great. And also, when we're averaging independent estimators, their variance goes down by 1 over m. So we get an estimator with better quality. So in the second application of shadow tomography, where we want to estimate the trace of our state with some observables up to error epsilon, here is a simple algorithm. We run our unbiased tomography on n copies, and this gives us an unbiased estimator rho hat of the state. Now, for each observable, OI, we're going to use the plugin estimator and compute the trace of the observable with the estimate rho hat. And this will give us some O hat I, some estimate of this trace. And it's not too hard to see that because rho hat is unbiased, the O hat estimates are also unbiased. And moreover, because now the observables are not over the entire density matrix, but they're just small scalars, they tend to have much better variance than the whole row hat. Moreover, some of you may have noticed that the measurement I performed was done before I knew the observables. I just ran tomography on the states without needing anything about the observables. So this actually solves a different problem called classical shadows or oblivious shadow tomography, in which you are restricted to performing your algorithm before the observables are given. So in our third application of multi-parameter quantum metrology, where we want to estimate the parameter given a parametrized state, well, this is actually outside the scope of this talk, since I will need to introduce a little bit notation, and maybe it's not enough time for that, but you're free to look at the paper or ask me later for more details. Okay, so now we have our three tasks that we want to find unbiased estimators for. And that was actually the original motivation for us in our prior work, where we introduced the first unbiased estimator for entangled tomography. And we called this estimator the debiased chaos because we obtained it by taking chaos algorithm, which was one of the known sample optimal but biased algorithms for entangled tomography, and we carefully modified it to remove its bias. So this turned out to be a very good idea because it allowed us to obtain improved or optimal bounds. And whenever it's improved, we conjecture optimality for these tasks. However, a caveat here is that actually analyzing this algorithm required a lot of representation theory and a lot of calculations. And the final paper ended up being more than 100 pages. So what is nice here is that using this random purification channel, we can obtain new unbiased estimators that are very easy to analyze and understand for entangled tomography. So let us see what is this unbiased estimator. So for this, we're going to use the second optimal, in a way, algorithm for pure state tomography by Hayashi. Unfortunately, this algorithm is biased. Fortunately, there exists a nice and simple modification that suffices to remove its bias that was introduced by Greer, Pashayan, and Schaefer, and we call this the GPS algorithm. And so now we can apply our mixed to pure state reduction to this GPS algorithm, in which we're given n copies of the state. We run purification to get n copies of a purification. And then we run the GPS algorithm to obtain an estimate sigma hat of this purification ket row. And finally, we're going to compute an estimate of the original mixed state by tracing out the second register of sigma hat. So let me convince you that this algorithm inherits the unbiasedness of the GPS algorithm. This is because the expectation of rho hat is equal to the expectation of sigma hat when tracing out the second register. And we can swap the expectation and the tracing out. And of course, sigma hat is unbiased. So expectation of sigma hat is ket brav rho. And tracing out the second register of the purification ket brav rho gives us the original state rho. So already, without too much work, we got a new unbiased estimator for entangled tomography. That's great. Moreover, when it comes to the quality of this unbiased estimator, it turns out that it matches the variance of our prior work on the debiased chaos algorithm. And I'm going to show you its second moment, which corresponds to its variance. Let me say first that you should be able to understand, I guess, most of this expression, maybe not intuitively, but most of these things make sense. Let me say that this L of lambda term will be explained a little bit later. So for now, bear with me. So even though this expression may seem intimidating at first, it's actually very easy to use, and in many different cases, as we will see in a bit. First of all, observe that it involves some nice matrices, the state row, identities, swap matrices. Let's actually go through all of the terms one by one. The first term is what we call the main term. If we had a perfect estimator, where rho hat is always equal to rho, then the second moment, rho hat tensor rho hat, will always be equal to rho tensor rho. For us here, we get something almost that. We get n-1 divided by n of rho tensor rho, so we're happy with this term. The second term is the main error term, and you can see that it scales with 1 over n, just like variances are supposed to do. So that's also a nice term for us. The third term is our second order error term, and you can see how there is an n squared in the denominator. This term then only matters when n is sufficiently small. However, it will be important for quasi-purification, as we will see later. Finally, the last term is the lower order error term. It turns out that this vanishes as the dimension of your space increases. However, even better for us, it turns out to be negative for all of our applications. So we can always just forget about it, and it only upper bounds our variance. So hopefully, at least on a high level, I convince you that it's clean and easy to use. And it's very nice because all of the learning applications that I have outlined and I will explain in a bit follow just from unbiasedness and from this second moment expression. As I mentioned before, getting exactly the expectation of L of lambda in this third term will require this quasi-purification modification to the original purification channel, and this will be something that I will talk about at the very end. Let's go to the first application of K-entangled tomography, in which we want to estimate our state when we only measure K copies at once. The theorem here states that a number of samples of d cubed divided by square root of K plus d squared and the whole thing divided by epsilon squared suffice to learn to trace distance epsilon, our state. And this matches the bounds for unentangled and entangled measurements. As you can see on the plot, when K equals 1, this matches measuring every copy separately. And we know that the right answer is d cubed. Whereas as the number of copies that we measure increases, the complexity decreases until it saturates at d squared, which is the optimal complexity. The previous work is by Zhandry and Liu that up to log factors obtained d cubed divided by square root of K. However, their bounds only held for small k. And one of the issues is because they didn't have an unbiased estimator, so they somehow had to embed one in the algorithms that they were using. Moreover, they were able to show a matching lower bound of d cubed divided by square root of K. And the conjecture for us here is that the bound that we obtain is actually optimal for all values of K. The second application of shadow tomography, where we want to estimate the trace of our state with some observables up to epsilon error, we show that a number of samples of log m divided by epsilon squared suffices in this high precision regime when epsilon is at most 1 over d. And there is a known lower bound, so our bound matches this lower bound and is thus optimal in this high precision small epsilon regime. And the previous work also achieved log m divided by epsilon squared samples. However, for them, the high precision regime was much more high precision. So it required epsilon to be much smaller, less than 1 over d to the 12. Of course, as I mentioned, our algorithm is oblivious to the observables, so we can obtain a more general bound on classical shadows. And this improves upon prior work by GLNM, and it also disproves a conjecture by Zhandry and Liu, where they had conjectured some bounds and were able to obtain a better upper bound than the conjectured one. In the third application of multi-parameter quantum metrology, where we want to estimate the parameter of a parametrized state rho of theta without wanting to introduce all of the context that I need to describe, there exists a well-known bound called the quantum Kramer-Rao bound. And using our unbiased algorithm, we can attain twice this bound, which turns out to be optimal. And the bound that we obtained was actually stated before in the quantum metrology literature, but without the proof. And then the author reached out to us to say it was nice that this was finally proven. But what is interesting is that our techniques are very different from the typical techniques that are used in this area. So it's nice how unbiased estimators for entangled tomography were able to help also in quantum metrology. And again, I invite you to see the paper for more details. So there is a last section on quasi-purification. Maybe I can pause here for a moment if there are any questions. Okay, so I think we can make it on time. So quasi-purification, why do we need an extension to the random purification channel? Well, let's recall the random purification channel for one copy. We calculated explicitly that purifying one copy is essentially adding a maximally mixed state on the second register. But then we're gonna perform pure state tomography on both the first and the second register, but the second register doesn't have any useful information. So performing pure state tomography on both of the registers is very wasteful. I mean, the second register is just useless. So and actually this can be made explicit if one calculates exactly the variance of the mixed version of our GPS algorithm using the standard purification, where one always purifies up to the maximum level. We can compute the second moment, and we get the following expression. And I don't expect you to remember the expression I showed you before, but you have to believe me that the only difference than the expression we got with the debias-Kaus algorithm is in the third term, in the second order error term. And the debias-Kaus algorithm had this mysterious expectation of L of lambda divided by n squared, whereas if we use standard purification, we get R divided by n squared. So to explain what this is, and then it turns out that this difference actually results in worse bounds for K-entangled and shadow tomography applications. And recall this is because the second order error term only matters when n is small enough. So when we perform K-entangled measurements, for us, n then is equal to k. So k can be quite small, and then this error term matters. Okay, so let me explain to you in a little bit more detail, but for this we need to understand the random purification channel. So recall Sure-Well duality. If we have n copies of a mixed state rho, this nicely decomposes into a direct sum over Young tableaus, lambda, of n boxes. And a quick primer on Young tableaus is a Young diagram has n boxes, and it's going to be arranged in R rows, where R is the rank of our state, even though some rows can be empty. And the rows have to be weakly decreasing. So the first row is the longest, and then they can only get shorter. And here we define L of lambda, this mysterious quantity, to be the number of non-empty rows, the height of the diagram. In our example here, this is the number of boxes in every row. And you can see here that R, the number of rows, is always at least L of lambda. And actually it turns out that in expectation, the height of the tableau that we get can be even square root of n. And thus, this term that we get of R over n squared, whenever we do no quasi-purification, can be much worse than the expectation of L of lambda term that we get in the debias-Kaus algorithm. So it is important for us to fix this and recover this expectation of L of lambda term. So how do we do it? What is quasi-purification? Let's look at very briefly the random purification channel. We're given n copies of a mixed state rho, we're going to measure in the Schur basis to obtain some Young diagram lambda. So once we obtain a Young diagram lambda, our state will collapse in one of these lambda subspaces. So it's going to be a tensor product of the lambda, some identity, and some other matrix. So now normal purification channel says that what you have now lives in d-dimensional space. To make it live in d times r dimensional space, you can append some registers in each tensor factor such that it lives in this bigger dimensional space. And it doesn't matter what exactly you need to append. It's not too hard to see if you read the paper. And what is this quasi-purification? Well, quasi-purification essentially modifies the second step. And instead of making every factor live in d times r dimensional space, it makes it live in d times L of lambda dimensional space. So this is kind of strange. The dimension of your output is decided after you measure. If you measure a very short tableau, you're going to purify in a smaller space. Whereas if you measure a very tall tableau, you measure in a bigger space. However, it's not too hard to check that still the resulting state lives in the symmetric subspace of dimension d times L of lambda. So it at least makes sense to perform pure state tomography since it lives in the same space. And that's actually the modification that suffices to get the optimal, the same variance as the debiased cows and recover the bounds that we get for all of the applications before. So that is the end of the technical content. And let me give you all with the conclusion. So we did a thorough study of purification in mixed state tomography. We recovered all the known results that we knew on mixed state tomography. And this hopefully establishes that the random purification channel is what we have to study when we're interested in mixed state tomography tasks. So since then, the random purification channel has been very busy, has been characterized analytically and applied to quantum Shannon theory, has been applied to channel tomography, extended to random dilation superchannels, applied to fermions and bosons, and many more things. And let me leave you with some future directions. The first one is, can we find more applications to the random purification channel? Most of the applications currently are learning-based, but maybe there is more things to do in testing, property testing, and so on. The second one is now our mixed GPS algorithm uses this bigger Hayashi measurement, which we don't know how to implement. And hopefully now we have enough motivation to study and find efficient implementations for this measurement, just how we were able to find efficient implementations of the GKKT measurement. And maybe one other direction would be looking back at the debiased cows algorithm. It was quite remarkable that we were able to get essentially the same variance, and the debiased cows algorithm analysis, even though long and laborious, things were always working out very nicely. Some miraculous constellations were happening. So it is worth considering whether there is some type of purification going on behind the scenes that we didn't know to look for. So we had to do the math the hard way. So to leave you, I don't know how to say it better than Felix Leditsky himself, that what you should do is for mixed state tomography, shut up and purify. Thank you very much for your attention.
All right. Thank you very much for very informative and wonderful talk. Yeah. Okay. So I guess we're running. Well, we did start a bit late, but I don't want to keep people too much longer than the scheduled time. So maybe a quick question or two from.
So I have one question.
Sure.
So do you have amplification toward cryptography? So in particular, somehow EFI, you must know EFI. EFI is very related to mixed state learning, and the one-way state generator is also related to pure state learning, right? And we can break one-way state generator by creating PP oracle. So can we apply this technique to breaking EFI by PP oracle? I don't know. This might be ridiculous question, but where the argument breaks down, do you have any comment about that direction?
This is not the direction that we have considered, so I don't know if I have anything to say off the bat. But yeah, it is an interesting question, certainly worth considering. And yeah,
I see.
if you're interested, feel free to email us, and we can look at the argument carefully and find if there is
I
a
see.
place where the argument breaks.
Thank you.
Yeah. No, thank you for the question. It will be interesting to see if it has any applications to cryptography, for sure.
Thank you.
All right. So do you have anyone else? I just want to clarify. So you mentioned that there's already like work on like channel tomography. So I'm assuming this is just a straightforward kind of application through the Choi operator, this kind of thing is how it would work.
Yes, so intuitively, it sounds very straightforward. Talking with some of the authors of the channel tomography works, there were a few maybe technical stuff needed to work out, just because learning in trace distance, the choice state doesn't translate nicely to a diamond norm in the channel. There is kind of a blow up in the error. So they had to use some specific properties of the pure state tomography algorithm to make it work. But at least
I see.
intuitively, it's the strategy you would expect, but the analysis had to be careful.
Yeah. Okay, John.
So is there some variation of this random purification to dilate, give Steinspring dilations of channels, random Steinspring dilations?
Yes, so actually, I think I had it here. Yeah, there has been work, and I guess it is one of the ways that you can get channel tomography by going through the dilation as well. My understanding, though, is that you can only lift kind of parallel uses of the channel. So it's still open whether you can lift adaptive uses of the channel using the random dilation superchannel.
So another thing I see from your paper that you can view your algorithm as a pretty good measurement.
Yes, well, every algorithm, whatever it does, is some type of a POVM. So it turns out that our POVM has a nice PGM viewpoint, yes.
Okay, so suppose instead of the PGM, you took the quadratic measurement where you square the densities, would you get a different algorithm? I guess your algorithm is nearly is essentially optimal anyway, so it doesn't matter.
Yeah, so I'm not familiar with the quadratic measurement. Yeah, so this is not something we looked into, but we can look into it.
Yeah, you cited this paper of Halevo for the pretty good measurement, but actually, if you look at that paper, he didn't introduce the pretty good measurement there. He introduced pretty good measurement with the density squared.
So you're saying that so the original pretty good measurement, you take your densities, you compute the sum of the densities, and then you take the inverse of the square root. So you're saying that instead he introduced squaring the densities, taking the sum, and taking the inverse of the square root.
And then but then putting the square of the density in the middle.
Putting the square of the density in the middle.
So it's just a pretty good measurement, but everything has been squared.
I see. Okay, I was not familiar of this measurement. Will be I have to read up into it to see what changes.
Okay.